Hey, so Julian Darden here. We're looking in Lab 1 for physics, constant velocity and motion. Purpose of this lab, we're exploring the concept of constant velocity in a one-dimensional direction, specifically the x vector. So we're looking whenever there's a zero net force, so that'll make the velocity constant. This will be shown in the data through tracker and Python graphs. If the slope of our graphs is constant, then that means the velocity is constant as well. In my video, I took a standard volleyball and rolled it across a flat surface of a table in my room. I set the axes from the center of the ball and the positive x direction being to the right, and calibrated the diameter of the volleyball as 0.21 meters. I used the center of the volleyball as best I could to use as my tracking point in that video. So I will show you my tracker analyzation right now. So here's the volleyball, and I've just let go of the volleyball right here. You can see the space between my finger and the ball. My axes were pushed right here as the positive direction to the right, and I have marked the center of the volleyball as my zero, as my origin. And the calibration for the ball comes a little later in the video, and I will show you that when it gets there. So as we play our video, you can see I marked the center of the ball as best I could, and I've calibrated it. Oh, passed it up a little bit. Calibrated the ball right here for 0.21 meters. It's pretty accurate. And then the video continues until the ball is about to fall off the table, and that is whenever I stopped the video. Here's the analysis from the video. The graph, well, here are the time in seconds all the way down throughout the video, and the position in meters all the way down. And this is the time versus position. And you can see the line is pretty constant slope, which is what we're looking for a constant velocity. And just a picture of the experiment here. So the analysis results. In order to code, I needed to find the initial velocity. So I have taken the second position we recorded and subtracted it from the initial position, and as well as the second time minus the initial time. That gives the initial velocity, and that's what we did here, to give us 0.7 meters per second. Now to begin with the coding, I inserted the ball's mass as 0.0267 kilograms, and initial conditions, the initial position of the ball on my axes was 0.004 meters in the x vector, x component, and the initial velocity, as we had just calculated, was 0.7 meters per second in the x component as well. I've set delta t for the loop as 0.01 seconds as a pretty accurate way to analyze our information. And also, my final time to stop the loop is at 1.68 seconds. That's how long it took the ball to go to the end of the table. I've changed the f-net vector to 0 as we were trying to simulate no outside forces acting on the ball. I've inserted Newton's second law here to calculate the ball's velocity in each loop. So the f-net, which is 0, is in here with the ball's mass times delta t. And then, for the ball's position at each time loop, we have inserted the same equation, and then obviously t is equal to t plus delta t. Now I will run the module for you to see. Calculating right now, should pop up, and you'll be able to see my ball goes from left to right, just like the video. And here's our graph. It's should be a very constant slope, which shows us that the velocity should be calculated as constant all the way through to 1.68 seconds. Here are the results from the Python versus the tracker graphs. The tracker graph are the blue dots that go up here, and you can see they kind of tail off at the end here as the velocity naturally slowed. And the red line that goes, you can see it's a constant slope, which is what was calculated through the Python graph. A reason that my experimented the volleyball line probably tailed off at the end. Obviously, there was some friction acting on the ball, so the f-net vector was not completely 0, although it was close. Maybe the slope of the table was not completely flat, and that could have affected the results. And the center of mass tracking, I might have clicked off of the center of the ball every now and then. But I would say we were pretty close to a constant velocity in the experiment. The Python graph and experimental graph were not too far off, so we can see that it's hard to simulate an f-net of 0 without the proper equipment, but we can get pretty close. Thank you for listening.